Welcome to the another lecture of design of RCC structure. In this class, we are going to discuss about a new topic, that is RCC slab. RCC slab is a very important structural component of any building structure, which is supported by beams and columns. In case of load transfer mechanism, slab is very important. For a building structure, load generally comes to slab. From slab, it's distributed to beam. From beam, it transfer through column to the footing. This is the load transfer mechanism of a framed building structure. So you can understand the slab is the most important thing. Now, example of slab, if we want to discuss, very easy example is in your house, your roof over your head, that is a slab, floor, that is also a slab. So this is a common, very easy example of slab. So from that example, you can understand that from top view, slab is a quadrilateral section. So it may be square, it may be rectangular. So actually there are two types of slab. First one is one-way slab, second is two-way slab. Okay. So this classification depends upon the ratio of longer span, that is Ly, and shorter span, that is Lx. As slab is a quadrilateral section geometrically, so it will definitely have two spans. It has four sides, that means it has two spans. One span is definitely longer, that is denoted by Ly, and shorter span is Lx, as I said earlier. So how could we define what type of slab one-way slab and what type of slab two-way slab? In case of design, we have some data, some design data to design. We have some load conditions, we have some section restrictions to design. From the given data, when we have to design a slab, first of all we have to decide this slab have to design in one way or two way. That is our first priority before slab design. So the conditions is Ly by Lx, that means longer span by shorter span, the ratio if greater than 2, in that case the slab will be designed as one-way slab. And Ly by Lx, that is longer span by shorter span, that means the ratio of these two span is less than 2, in that case the slab will be designed as two-way slab. Let's check first a pictorial view. This is a pictorial view to differentiate between one-way slab and two-way slab. The figure number 1 is one-way slab. Look, shorter span is denoted by Lx and longer span is denoted by Ly. And in figure 2, that is two-way slab. So Ly by Lx, this ratio if greater than 2, then one-way slab, and Ly by Lx, if the ratio is less than 2, then it will be designed as two-way slab. Let's have a look at the definitions of one-way slab and two-way slab. One-way slab in this type of slab, bending takes place only along shorter direction. Therefore, the main reinforcement is provided along the shorter span and distribution bars are provided only longer span. So, this is the definition by which you can understand what is one-way slab more easily. Now, in case of two-way slab, in this type of slab, bending takes place in both directions. So, the main reinforcement is provided along both directions. So, this is the basic difference between one-way slab and two-way slab. In case of one-way slab, bending takes place only along one direction, that is shorter direction. But for construction, we have to provide reinforcement bar in longer span also. That reinforcement is called distribution bar. So, in case of one-way slab, along the shorter direction, main reinforcement is provided, and along the longer span, distribution steel are provided to make the mesh and construct the slab. But in case of two-way slab, both sides, in both direction, we have to provide main reinforcement bar because bending takes place in both sides in this case. Rather than that, in case of two-way slab, we have to provide corner reinforcement in four corners of that slab to resist torsional moment. So that will be discussed when we will design two-way slab before that. But in this lecture further, we will discuss about one-way slab because in this lecture we will design one-way slab. So let's start the design. So this is the problem which you can see in your screen. So let's read out first the problem. Okay, look, here is written in note copies one-way slab, but when you get question in your exams, so that is not written that it is one-way slab or two-way slab. We have to find out that the slab from the given question, the slab have to design as one-way or two-way, and the criteria you know that the ratio of longer span and shorter span. So let's start this problem. The question is, design a floor slab size 3 meter by 6.2 meter for a living room of a residential building. Take live load as 4 kN per meter and floor finish as 1.5 kN per meter. Use M20 concrete and Fe 415 steel. Bearing is 300 mm. So this is the question. As I said in earlier lectures also, when you get a question, first read out it very carefully. Okay. So size of beam is given, live load is given, floor finish is given, grade of concrete, that is M20, is given, grade of steel, that is Fe415, is also given, and bearing is given. You know the bearing. What is bearing? I have discussed in the lecture of single reinforced beam and double reinforced beam also, that what is actually bearing is. Bearing is as if the slab is supported on beam or supported in over wall. So half of this section, half of the support, for half of left support and half of right support, that is equals to one bearing. So one bearing, the value of one bearing will be bearing means, that means support, and value of one bearing is support length. Okay. One another thing which I forgot to tell you before, but before starting the design we have to know it, that slab is analyzed by assuming it to be a beam of 1 meter width. This is written in IS code also. Slab is analyzed always by assuming it to be a beam of 1 meter width. So design procedure of slab is almost like beam, because we have to design it as 1 meter width beam, that means 1000 width beam. So let's start the design. So first of all, write down the given data. Longer span, that is LY, is 6.2 meter. Shorter span, that is LX, is 3 meter. Live load is 4 kilonewton per meter. Floor finish is 1.5 kilonewton per meter. One bearing is 300 mm. FCK is 20 MPa. Fy is 415 MPa. MPa means Newton per millimeter square. You know that. So all given data are written here from the question. So next we have to decide the slab is one way or two way. For that we have to check the ratio Ly by Lx, that is equals to 6.2 by 3, that is equals to 2.06. So this is greater than 2, and as per the condition this slab should be designed as one-way slab, and shorter span will be take in consideration for design. So along the shorter span we have to provide the main reinforcement. Okay, so let's start the design. First we will check for depth. We will decide the depth. Actually we have to provide the depth, after that we will check. So this is just like beam section design. So there are two ways to decide that. First, span by effective depth, that is equals to basic value into modification factor. Now, so from this we can easily find out the depth. So d is equal to small d, that is effective depth, that is equals to span by basic value into modification factor. So span is 3 meter, shorter span, as shorter span is in consideration. Shorter span is 3 meter, that means 3000 mm. Now basic value is 20 and modification factor 1.5. Basic value is 20, we get it from clause number 23.2.1 of IS 456. We seen it before, and the basic value is given there for simply supported beam is 20. As slab is designed as beam, we have to take that value. Now modification factor you have to assume. So there are no such as strict rule, just you have to assume. You can do it like this. So this is come 100 mm, and there is another method. You can do like that, this also. D is L by 25. Simply you can use this thumb rule. D is equal to L by 25. L means span, and in consideration the span is 3 meter, 3000 mm. So 3000 by 25, that is equals to 120 mm. For safety we assume some larger value, so that is equivalent to 125 mm. So now in our consideration, our assumption, the depth, the effective depth of slab is 125 mm. So the overall depth, capital D, is obviously is equals to small d, that is effective depth, plus clear cover plus half dia of bar. So effective depth is 125 as we consider. Clear cover we give 20 mm, and if we assume 10 dia bar will be given, in that case we can assume 5 mm is half diameter. So overall depth is 150 mm. That will be checked later. Now effective span of slab. For effective span, from clause number 22.2 of IS 456 2000, list of the following will be taken: either length span plus effective depth, that is equals to 3 meter plus 0.125 meter, that is equals to 3.125 meter. 0.15 meter is effective depth, we know that's 125 mm, or effective length is equals to span plus one bearing is 300 mm is given, that means 0.3 meter. So 3 meter plus 0.3 meter, that is equals to 3.3 meter. So list of these is 3.125 meters. So L effective is equals to 3.125 meter, that is taken. Now let's check once the clause number 22.2, whatever is I have written here, it is right or not. Let's check clause number 22.2 of IS 456 2000. So let's go to code. Look here, clause number 22.2, effective span. Simply supported beam or slab, the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of slab or beam or center to center support, whichever is less. We have did that there. So let's go to notes again. Now the next step is load and moment consideration. First of all, we have to calculate the dead load. To calculate dead load, we know we have to multiply cross section of the slab with unit weight of RCC. So length into depth into unit weight of RCC. So dead load is 1 into 0.15 into 25. 1 means 1 meter, that is, as slab is designed as 1 meter with beam, so that is always 1 meter or 1000 mm for slab, and overall depth is 150 mm, so that is 0.15 meter into 25 kilonewton per cubic meter is unit weight of RCC, so that is equals to 3.75 kilonewton per meter. Floor finish is given, that is 1.5 kilonewton per meter, and live load is also given, that is 4 kilonewton per meter. So total load is equals to 9.25 kilonewton per meter. So factored load W is equals to 9.25 into partial safety factor 1.5, which we can get from table number 18 of IS 456 2000. So that is equals to 13.875 kilonewton per meter. So factor moment mu is equals to 13.875 into 3.125 square by 8, W square by 8, you know the formula. So that is equals to 16.93 kilonewton meter. So now next is depth check of slab. So to check the depth, we have to use the formula for limiting moment, which we can get from Annex G of IS 456 2000. So mu limit is equals to 0.36 into xu max by d into within bracket 1 minus 0.42 xu max by d bracket close into fck into b into d square. This is the formula which was written in IS 456 2000 Annex G. So we have our value for moment, ultimate moment, that is 16.93 into 10 to the power 6 equals to 0.36 into xu max by d. This is 0.48 for 415 grade steel within bracket 1 minus 0.42 into 0.48, that is the 0.48 is the value of xu max by d for 415 grade steel, bracket close into fck, that is 20, and b is 1000 because slab is designed as 1000 mm width of beam, into d. This d value is unknown here because this is the required depth. So from this equation we can find out the value of d, small d, that is equals to 78 mm, which is less than 125 mm, which we have already considered. So the depth is safe, depth 125 mm which you consider is safe. Now the next step is calculation of steel. For calculation of steel, we have to use the formula for mu from Annex G of IS 456 2000, and the formula is mu is equals to 0.87 Fy into AST into D within bracket 1 minus AST into Fy by Fck into B into D bracket close. If we put all the values except area of steel, then we will get the area of steel, that is AST. As you see here, all the value have been put here, like mu is 116.93 into 10 to the power 6 is equals to 0.87 into Fy is 415 into AST into D effective depth is 125 within bracket 1 minus AST into Fy, that is 415 by Fck, that is 20 into 1000 into 125. So from this equation we can get this value of AST, that is 401.96 mm square. Now provide 10 mm diameter bar as main reinforcement. Spacing. So spacing is equals to area of one bar by area required into 1000, as 1000 is taken bar area per width of bar. So that is equals to area of one bar is pi by 4 into d square, and here diameter is 10, so 10 square, by required area is 401.96 into 1000, that is equals to 195 mm. We have the license to reduce the spacing, so that is equals to, we may write 190 mm. Now spacing should be least of the following. This is as per clause number 26.3.3, 3 into effective depth, that is equals to 3 into 125, that is equals to 375 mm or 300 mm, or which we get from here 190 mm. So from these three, least value is 190 mm, so spacing is 190 mm center to center. So this criteria is written in clause number 26.3.3. Let's go to the code and check out this clause. Look, clause number 26.3.3 B, slabs. The horizontal distance between parallel main reinforcement bars shall not be more than 3 times of effective depth of solid slab or 300 mm, whichever is smaller, and whatever we have calculated there. So from these 3 value, the least amount which we already take. So let's go to notes. So as per clause we have did it as you seen in IS 456. Now the AST provided is pi by 4 into 10 square by 190 into 1000, that is equals to 413.367 or 413.37 mm square. This is the provided AST. As we have reduced the value of spacing. So provided steel area is increased. But there is a condition of minimum reinforcement and maximum reinforcement in clause number 26.5.1.1 under table 16A. AST minimum is 0.85 BD by Fy equals to 256 mm square. This is the minimum reinforcement has to be provided for this section, and AST maximum is equals to 0.04 B into capital G, that means overall depth, that is equals to 6000 mm square. So the value of AST provided is lies between this minimum and maximum, so hence this is okay. So we can provide 10 mm main reinforcement bar along shorter direction at the rate of 190 mm center to center. But let's check once the clause number 26.5.1.1 this condition. Okay, let's go to the code. So look here, AST by BD is equal to 0.85 by Fy. So from here a value of AST is equal to 0.85 BD by Fy. From that formula we have already calculated, and this is the minimum requirement of reinforcement, and the maximum requirement of reinforcement is the maximum area of tension reinforcement shall not exceed 0.04 BD. So as per our calculation, the area of steel provided lies between these two values. Let's go to notes. Now next step is distribution steel. For distribution steel, first of all we have to check out once clause number 26.5.2.1 of IS 456-2000. Let's go to code. Now check here clause number 26.5.2.1 minimum reinforcement. The mild steel reinforcement in either direction in slabs shall not be less than 0.15% of the total cross sectional area. However, the value can be reduced to 0.12% when high strain deformed bars or welded wire fabric are used. In this case we are using HYSD bars, so the second value 0.12% of cross sectional area will be used. Let's go to notes and check. So see here, as per clause number 26.5.2.1, area of distribution steel which is denoted by ASTD is equals to 0.12 into BD by 100, that means 0.12% of cross sectional area. So if we calculate 0.12 into 1000 into 125 by 100, that is equals to 150 mm square. So this is the area of distribution steel for this case. So we can use 8 mm dia bar. Here we are using 8 mm dia bars. So spacing is pi by 4 into 8 square by 150 into 1000, that is equals to 335 mm. So we can reduce the spacing, will be then 300 mm. So now maximum spacing is 5G or 450 mm as per clause number 26.3.3. So maximum value is this. So we have calculated, our calculated value is 300 mm. So therefore provide 8 mm dia bar at the rate of 300 mm center to center along longer span as distribution steel. So distribution steel part is also complete, but check once the clause number 26.3.3 about the spacing conditions. So look here, clause number 26.3.3 maximum distance of tension bar, B2, the slabs, the horizontal distance between parallel reinforcement bars provided against shrinkage and temperature shall not be more than 5 times the effective depth of a solid slab or 450 mm, whichever is smaller. So our value is already less than that. We have provided the 300 mm spacing. So design is almost complete. Now we have to check. Our first check is deflection check. So from clause number 23.2.1 and figure 4 of IS 456, we know to find out modification factor, first of all we have to use the formula of Fs, which is just below figure number 4 of IS 456-2000. The formula is Fs is equals to 0.58 Fy into AST required by AST provided. So that is equals to 0.58 into Fy is 415 into AST required is 401.96 by AST provided is 413.37. We know these values. So that is equals to 234.056 or this is equals to 234 Newton per millimeter square. Now percentage of steel is AST provided by cross sectional area, that is B into D into 100. So that is equals to 0.33%. We know to find out modification factor from figure 4 of IS 456-2000, we have to know two values, that is Fs value and percentage of steel. From these two values we have to find out the value of modification factor. So let us go to figure 4. You can see in your screen figure 4 of IS 456-2000. So our Fs is 234 Newton per millimeter square, but there is no curved line of 234, but 234 is lies between 190 and 240. So we have to interpolate from these two lines. So first check for Fs 240 and percentage of steel 0.33, the value of modification factor is almost 1.5. You can check this value with the help of pencil or scale. And for Fs 190 we can assume the value of modification factor 1.9. So now we have these two values. From these values we have to find out the value of modification factor for Fs 234. So in your screen now you can see, so whatever our findings as per figure number 4 of IS 456-2000, for Fs 240 modification factor is 1.5 and for Fs 190 modification factor is 1.9. Therefore for Fs 234 modification factor is equals to 1.9 minus within bracket 1.9 minus 1.5 by 240 into 190 into 234 minus 190, that is equals to 1.9. So modification factor is 1.9. So effective depth is equal to span by base value into modification factor. Base value as per this clause is 20 for simply supported beam, as we see it earlier of this problem, early stage of this problem when we are considering the depth. So basic value is 20 multiplied by modification factor, whatever we find out, that is 1.9. So this is equals to 75. So required depth is 79 for deflection, to resist deflection, but our value which we have already considered is greater than that, that is 125 mm. So this is safe in deflection. Now check for shear. to check shear, first of all we have to find the value of shear force, that is Vu, that is equals to WL by 2. This is written in clause number 40.2.1.1 of IS 456/2000 in page 72, but we already know that the value of shear force, to find out the value of shear force we have to use the formula WL by 2. So that is equals to WU, we have calculated the 13.875 into L is 3 by 2, that is equals to 20.81 kilonewton. Now nominal shear stress tau V is equals to V by BD. B is 20.81, which we have calculated just now, by B is 1000 into D is 125, that is equal to 0.16 MPa. Now value of tau C from table number 19. So from table number 19 we have to find out value of tau C. Okay, so let's go to table number 19. After that we will get back here. So we know a percentage of steel is 0.33. So let's go to the code. Now this is table number 19 of IS 456/2000, design shear strength of concrete tau C in Newton per millimeter square. So first column is 100 AST by BD, that means percentage of steel is 0.33 is in our case. There is no value for 0.33, but 0.33 is lies between 0.25 and 0.5. Our grade of concrete is 20, so 0.25, the design shear strength is 0.36 MPa or Newton per millimeter square, and 0.50 percentage our grade of concrete, when our grade of concrete is M20, the value of tau C is 0.48. So for percentage of steel 0.33 and grade of concrete M20, the value of tau C will be definitely lies between these two value 0.36 and 0.48. We have to find out that with interpolation method. Let's go to code, go to notes. So now look, the value of tau C from table number 19, as you see we have to interpolate. So value of tau C is 0.36 plus 0.48 minus 0.36 by this will be 0.5, not 0.75, mistakenly written here. You should when you note down this, you should write in your notebook. This will be not 0.75, this will be 0.5 minus 0.25 into 0.33 minus 0.25, that will be equals to 0.34 Newton per millimeter square or MPa. Now in case of slab we have to multiply a factor with tau C value to find out design shear strength. The K value we can get from clause number 40.2.1.1. So let's check this clause. Now look, clause number 40.2.1.1 of IS 456/2000, for overall depth. Now for solid slab, the design shear strength for concrete shall be tau C into K, where K has values given. So these are the depth: 300 or more, 275, 250, 225, 200, 175 and 150 or less. Our overall depth value is 150, so the K value will be 1.3 for us. Let's check the calculation. So K tau C is equals to 1.3 into 0.34, that is equals to 0.44 Newton per millimeter square or megapascal. So tau C is less than K tau C, hence safe in shear. That means no shear design required for this case. Okay. So let's go to next step. So next step is development length check. For development length check, we know we have to go to clause number 26.2.3.2 4.3, page 44. From this clause we will get the formula m by v plus L0 is greater than LD. So let's check the formula first from code. So here is the formula in page 44, m1 by v plus L0 that should be greater than LD. So for LD in clause number 26.2.1, it is the formula for LD. We have seen the formula and detail in my previous lecture for single reinforced beam, which link is given in description box. You can check that there. The value of tau BD is given here in clause number 26.2.1.1. For grade of concrete M20, the value will be 1.2, and for deform bar it shall be increased by 60%, right? So let's go to notes and check it how these all are applied in design problem, in solving design problem. So here it is, dia into 0.87 Fy by 4 tau BD, that is equals to 10 into 0.87 into 415 by 4 into 1.2 into 1.6, that is 60% increased what we have read just now in IS code, right? So the value will be 470.11 mm, and L0 is either 125 mm or 12 into diameter, so that is 120 mm. So L0 is 125 mm. So m by v plus L0, that is equals to 16.93 into 10 to the power 6 by 20.81 into 10 cube plus 125, that is equals to 938.55, which is greater than LD. That means this is safe in development length. The next step is we have to write the design data. So all design calculation is done. We have already checked, we have completed the all checkings. So now time to write design data. After that we have to draw it. So capital D, that is overall depth, is 150 mm, small d effective depth is 125 mm. Main bar along shorter span is of 10 mm at the rate of 190 mm center to center. Distribution steel bar along longer span is of 8 mm dia at the rate of 300 mm center to center, and actual cutoff is 300 mm from the center of support. So let's check the drawing. This is the drawing. So main bar is 10 mm dia at the rate of 190 mm center to center, and distribution steel is 8 mm at the rate of 300 mm center to center. So here the solving of problem for one-way slab is end. That's all for this lecture. Thank you.